Okay, Assalamualaikum. Salam sejahtera. Nama saya Fairuz. Saya akan mengajar, will teach you on the transform circuit uh, course or subject. Okay, it's called BEV20203. So this is chapter 1, signal representation and mathematical operation. Um, so this first chapter is very important that you need to fully understand, because we are going to use this chapter throughout the entire course. So you really need to understand and master this signal, drawing of the signal, representation of the signal in mathematical equation, because we are going to use this in chapter 2, 3, 4 and 5 and so on, right? Okay, chapter overview. First, we are going to look at the mathematical representation of signals. So we will look at sinusoidal, for example, step, exponential, and impulse. Then we will look at the terminology and units, frequency, amplitude, wavelength, period, and power. So definitely you have learned this before in different subjects, but we will go through this again. Okay, just to recall on these terms, this terminology. Next is we will go to graph plotting, which is we will learn how to plot this graph. All right, and then we will do mathematical operation on some of these signals. If signal A is multiplied with signal B, what is the result? Signal A plus signal B, what is the result? So we will need to learn this in chapter 1. Okay, mathematical representation of signals, piecewise function. A function can be in pieces. So the term piecewise function means that a function, a mathematical function, can be in pieces. You can put them in separate pieces. Example here, this is example of piecewise function, right? So it says 1, 2, 3, 3 pieces. So you can write mathematical function in this format. So it has, for example, this case it has 3 pieces of graph, right? x2, 6 here, just a single dot, single value at fx. This is fx is equals to y, right? So this is y. So y is 6 if x is 2. So x is 2. So 6, x is 2, right? Then y or fx is 10 minus x is a straight line. Okay, y equals 10 minus x, right? So y equals 10 minus x is actually a very long line, infinity, from infinity negative to infinity positive. However, if we have, when we have this, the limitation, right? So this is only from x equals 2 to x equals 6. So from here 2 to 6, right? So from here to here only, right? Same goes to x equals x squared. Okay, this is the function of x squared, right? But this goes to negative infinity, this goes to positive infinity, right? But it says here if x is, if only for x less than 2, right? So meaning this is only true starting x equals 2, right? Meaning from here x equals to negative infinity. Alright, so that is the piecewise function. So it has this fx or y exists. It has this function, alright, x squared 6 10 minus x. It can be just 2, or it can be more than 10 even, right? And this is the limitation for each of the function. Alright, so we can create functions that behave differently based on the input x value. So before this, instead of just having one graph in a figure, we can draw multiple graphs in one figure using piecewise function. Alright, so next, mathematical representation of signals. Okay, the unit step function or Heaviside function, right? In engineering applications, we frequently encounter functions whose value change abruptly at specified values of time. One common example is when the voltage is switched on or off in an electrical circuit at a specified value of time. Alright, so meaning that unit step function is very common in engineering applications, right? The value of t equals 0 is usually taken as a convenient time to switch on or off the given voltage. So let's look at the waveform. So this is the Heaviside function or unit step function. It's from 0, switch on, goes to 1, right? So this is what it means. Whose value change abruptly at a specified value of time t. Okay, so t can be 0, right? But t can also be a different value. All right. All right. So same thing. Unit step function. How can we draw this in piecewise function? Right. So we see here we have 0, y equals 0 for t less than 0, and then y equals 1 for t more than 0, right? So you can see here, in this case it's called ut. Okay, ut, this is the ut. Okay, sorry, difficult to draw using mouse. All right, so this is y-axis here is the ut, right? So 0 here for t less than 0, and then ut is 1 for t more than 0. That is u is a function of time t, and u has value 0 when time is negative. All right, before we flip the switch, turn on, turn off the switch. Right, and then let's go to the next step. Shifted unit step function. Right, shifted unit step function. In many circuits, waveforms are applied at specified intervals other than t equals to 0. Such a function may be described using the shifted, aka delay. Okay, shift or delay. Right. So here, instead of t, right, the switch happens at t equals 0, right, instead of that. So the switch happened at t equals a. So a can be any value, 1, 2, 3, or even negative 1, besides 0. Okay, so if the shift or the switch from 0 to 1 happens at t equals a, for example, then we can just simply change this to a, right? Change this to a, where the switch is happen, and then instead of u equals t, ut in bracket, okay, you have u t minus a. So this is the shift. This is the shift of the unit step function. All right, so if this is positive, then this is in negative value, right? Do not mistake that. Okay, example, let's look at example. All right, so we have a function of u t minus 3, right? Means that it's a shifted unit step function at t equals 3, okay, positive 3. Before that is 0, after that is 1. Simple as that, right? So if t is plus 3, so it happens here at negative 3. All right. Right, next is rectangular pulse. Okay, rectangular pulse. A common situation in a circuit is for the voltage to be applied at a particular time, say t equals a, like a shifted unit step function, and then remove later at t equals b, for example. All right, so we have from 0 and at a goes to 1, and then at b goes back to 0. So this is rectangular pulse. All right, so in terms of mathematical representation of this signal, we use this. Okay, so ut minus a is this, right? And then ut minus b will cause this. Okay, I say will cause because ut minus b is not like that. All right. Okay, I'll try to draw here. Okay, ut minus a is this, right? And then we have minus or negative ut minus b. Means that, sorry, this is a, or this is a, right? And this is b. So b is like this. So this is at a, this is at b, right? Okay, so this is ut minus a from 0 to 1 at a, and this is negative ut minus b, inverse. So this is start from what do you call it, start from, sorry, I think it's a bit confusing if I do like this. Okay, sorry. All right, this is a, all right, and then this here is b, right? So if these two signals we subtract or minus, then okay, this is at 0, this is at 0, so 0 0 is 0, this is 1, this is 0, is 1, okay, this is 1 minus 1, we have 0. Okay, right? So this is what mathematical representation of the rectangular pulse. Okay, so please understand the concept of this, because later on it will be much difficult. Right, example, second example, right? So ut minus 1.2, this is 1.2 here, and then just change color. Ut minus 3.8, 3.8 is here, right? So these two signals, red and blue, if we subtract, we'll get 0 0 0. 1 1 0 is 1, 1 1 is 0, right? So the duration is 2.6 here.